Alright, so now we have learned the concept of effective stress and the effective stress equation. I'm going to present a number of calculation examples for total stress, pore pressure, and the effective stress along a given soil profile, for a given soil profile. For the first example, this is a two-layered soil profile. We have layer 1 that's above the groundwater table. So you're going to use the moisture unit weight for stress calculation. Layer 2 is below the water table, so the soil is fully saturated. So I'm going to draw the distribution of total and effective stresses as well as pore pressure. First, let's start with total stress. So this is total stress. So for total stress, at the ground surface, it's 0. And then at point A, that's 10 feet below the ground surface, this total stress is the moisture unit weight, 90, times the depth of this first layer, which gives us 900. And then at point B, so the total stress value at point B is 900. So that's the contribution from the first layer plus, for second layer, we're going to use the saturated unit weight 110 times its depth, which is 20. So this gives us 3100. Then you just need to connect these points to get the profile of total stress along depths. And then for pore pressure, the pore pressure is 0 for the first layer because it's above water table. So it's going to be just a vertical line here. And then at point B, the pore pressure is the unit weight of water, 62.4 times the depth to the water table, that's 20. This is 1248. And you just connect again these 2 points. So that's the pore pressure. Finally, the effective stress is the difference between the total stress and pore pressure. At the ground surface, sigma prime is 0. At point A, sigma stress is 900, same as the total stress. So this is sigma A prime equals to 900. And then at point B, sigma B prime equals to 3100, that's the total stress, minus pore pressure 1248. And you get 1852. So that's sigma B prime at point B. So you connect these points, you get the profile of these stress values along depths. And then finally for part B here, so we're going to calculate the effective stress at B, so that's sigma B prime using the buoyant unit weight. But here you need to be careful. The buoyant unit weight only exists for soils below the water table. So the sigma B prime for layer 1, you're still going to use the the moist unit weight because it's above groundwater table. There's no buoyant unit weight for first layer. So still 90 times 10. So this is gamma m. And then for the second layer, because the soil is below the water table, this is where you can use the buoyant unit weight, which is 110 gamma saturated minus 62.4. That's your unit weight of water times the depth. So this is gamma saturated of layer 2, and this is gamma water. Okay. So this difference here is the buoyant unit weight. And If you just work out the math here, you still get the same number, 1852 pound per square foot. Okay. So this is the same as if you're using the effective stress equation. Part C, D, and E of example 1 deal with the change in effective stress at point B if water table changes. So we're going to look at 3 scenarios. The first one is water table drops by 5 feet. So this can be caused by, for instance, dewatering during a construction project. Part D is the case where water table rises to the ground surface. And part E is the case where water table rises to 5 feet above the ground surface. And the original effective stress at point B that we calculated from part A is 1852. Okay. So we're going to look at part C first. So if the water table drops by 5 feet. So shown here, so this is part C. So if a water table drops by 5 feet, so we have 10 feet of moist soil. Then we have additional 10 feet of 5 feet of moist soil. And then 15 feet of saturated soil. Okay. So that's the new soil profile. And the effective stress, sigma B prime, equals to 10 plus 5, so that's 15 feet of moist soil. So for moist soil, there's no buoyant unit weight. So we use the moist unit weight to calculate effective stress. Then plus 15 feet of saturated soil. So for saturated soil, the effective stress is height times the buoyant unit weight, which is gamma saturated minus gamma water. Okay. This is 90 PCF. Gamma saturated is 110 PCF, and water is 62.4 pound per cubic foot. So if we're plugging all these numbers, the effective stress at B after the water table drops is 2064 PSF. Then the change in effective stress delta sigma B prime is sigma B minus the original effective stress. So this is original at point B. So that's 2064 minus 1852. And this is 212 PSF. So this means after the water table drops by 5 feet, the effective stress increases by 212 pound per square feet. Increase. So for part D, the water table rises to the ground surface. So this case, for this case, all the soils are saturated. So you have a total of 30 feet of saturated soil. And for this case, the effective stress, so this is part D. The effective stress at point B is simply the height of this saturated layer, 10 plus 20, times the buoyant unit weight, gamma saturated minus gamma water. And if you plug in these unit weights, you get 1428 PSF. So that's the new effective stress at point B. So the change delta sigma B prime is sigma B prime minus sigma B original. And this equals to 1428 minus 1852. And that's negative 424 PSF. You get a negative. This means that the effective stress after water table rises to the ground surface actually decreases by 424 PSF. Decrease. finally, for part E, the water table rises to 5 feet above the ground surface. So this is a ground surface. This is ground surface. So in this case, what is the effective stress at point B here? To calculate this, we're going to use the effective stress equation. So we're going to calculate the total stress at B, the pore pressure at B, then take the difference to get effective stress. So for part E here, sigma B prime, that's the effective stress, is sigma B total minus pore pressure at B. For total stress, remember total stress is defined as basically the total weight above that point over unit cross-sectional area. For point B, the total stress includes 5 feet of water. That's the water above ground surface. Then you have 30 feet of saturated soil. So that's 10 plus 20. Saturated. So that's your total stress. Sigma B. And then the pore pressure is simply the height of the water to that the water table. That's 35 feet times unit weight of water. So this part is U sub B. And if you plug in numbers, so you will get 562.4 plus 10 plus 20, 110 minus. So if you look at the last term here, it's actually, you can put it as 5 times 62.4, which is, this is basically that 5 feet of water above ground surface, and then 30 feet of water beneath the ground surface. So this first term and third term, they cancel each other out. So left with 30 times, so let me actually replace this by number. So this is 62.4. So this is 30 times 110 minus 62.4. Okay. So if we compare with what we get from part B, this is actually the same as the effective stress we calculated from part D. So that's 1428 psf. Okay. So then the change in effective stress, sigma delta sigma B prime, is 1428. That's the new effective stress minus the original one, 1852. Again, we get negative 424 psf. And this is the same as part D, so the effective stress decreases. And also, if you compare part D and part E, you realize that if the water table changes above the ground surface, the effective stress actually stays the same. So you get 1428 from part D, and if the water table rises 5 feet up over the ground surface, the effective stress stays the same. So the second example here is very similar to the first one. We also have a two-layered soil profile. Groundwater table is at the top of the second layer. And the difference here is that for layer 1, we are given dry sand unit weight, gamma dry. So I'm going to work through this problem relatively fast. For total stress, again, we have 0 at the ground surface, and then at point B, because we're given dry sand, so we're going to use the dry unit weight, 16.5, times the depth of the first layer, 6, that's 99. And then for point C, the total stress at point C is 99, that's from the soil layer 1, plus the unit weight of the second layer, saturated unit weight of second layer, 19.25 times the depth of the second layer, 13. So that's 349.25. And then you connect these points to get total stress profile. For pore pressure, 0 at the ground surface. And for layer 1, pore pressure is 0 because it's dry sand. And then for point C, that's the bottom of the second layer, pore pressure is unit weight of water. In this case, we are using the SI unit. So that's 13 times, we're going to use 9.81 times 30 meter. And that's 127.53. So that's the pore pressure. And for effective stress, that's the difference between total stress and pore pressure. So 0 at the ground surface. At point A, it's 99, same as total because pore pressure is 0. And then at point C, effective stress is 349.25 minus 127.53, and that's 221.72. And if you connect these dots, you get effective stress profile along depths.